Hi, folks. We've been talking about Newton's laws, and now we want to talk about chapter 6, which is applications of Newton's laws. How we use what we understand about forces to describe or explain what is going on and give us a better model of how we use them. One of the types of forces that we use is friction. Friction is defined as a force that opposes motion. This can be a moving object or a stationary object. In other words, the friction on a stationary object keeps it from moving. So we're going to look at primarily the friction between two surfaces that are sliding against each other. There's other types of friction like air resistance and water resistance, but this is the one that we have the easiest way to compare to. And that surface friction between two surfaces is there because those surfaces are very rough microscopically. Now, we can cause the friction to diminish if we smooth out those surfaces and have less interaction between the hills and valleys of one surface to another. But it depends on the two substances that are in contact with each other. Interestingly enough, if you smooth the surfaces out too much, you will actually have electrostatic interaction where the electrons and protons of one substance are attracted to the other substance. So it can build up this friction again when you have ultra smooth surfaces. When we talk about the sliding friction on an object, we talk about friction in two different ways, static and kinetic. Static means stationary and kinetic means moving. So right here we have two situations where there's a static friction force and one situation where there's a kinetic friction force. And the difference is that the two situations where there's a static force, there's a force being applied to something, but it's not enough to move it. All right. We notice with these four diagrams, the first one, there's no friction. There are two forces acting on the block. One is gravity, and which is the weight, and one is a normal force from the surface. It's equal and opposite to the weight because it's a horizontal surface. But the second diagram here, we're pulling to the right, the block is not moving. That means there's not enough force to cause it to overcome the static friction. The static friction force will increase for a given situation until it reaches a maximum. And that's what we have this inequality here. The zero is less than or equal to Fs, which is less than or equal to Fs max. All right. That tells us that the static friction force changes for a given situation until it reaches the maximum. At the maximum, that's when the object that is having the friction applied to it breaks free. So that's when it starts moving. Now it's no longer static friction, it is kinetic friction. And that's what we see on the bottom diagram here, where the kinetic friction force is acting in the same direction the static friction force was, but now it's moving. We have the velocity has a value to the right, and the force pulling it to the right is equal to the kinetic friction force. Notice our arrows are less than the Fs in the diagram above it, which means typically the kinetic friction force is less than the maximum static friction force. All right. This formula right here with Fs max equals mu s times n. Mu is a Greek letter. We use that to indicate the coefficient of friction. So we have a mu s and a mu k, one for static, one for kinetic. And it just tells us how much we have to multiply to the normal force to know how easy it is to start something sliding or to keep it sliding. So I like to use start and keep instead of static and kinetic sometimes because they are kind of interchangeable. So mu s is the multiplier to the normal. So if I know how much it is to lift something, which is equal and opposite to the normal on a horizontal surface, I just have to multiply that by mu to figure out how easy it is to slide it. The break-even point is when mu is 1. If mu is 1, that means it takes just as much force to slide it as it does to lift it. If mu is less than 1, it's easier to slide something than it is to lift it. If mu is more than 1, it's more difficult to slide it than it is to lift it. So mu can be defined as a ratio of the difficulty to slide versus the difficulty to lift off of a horizontal surface. If it's not horizontal, then we can't measure it as easily. All right. Couple things to note, like it says on the bottom right here, the static friction force is independent of area of contact of the surfaces. That is not what people think. People think the bigger the area, the more force it takes to slide something. That's not true. It takes more force when we have certain combinations of materials. The coefficient of friction varies based on the combination of materials, but not the area, the surface area that is in contact. All right. So the kinetic friction force is the force that once something is moving, how much force it takes to keep it moving. All right. So we have the same exact formula, Fk equals mu k times the normal, and that gives us the ratio. So we can also, if you look at this here, if we have an object and we're putting a force on that in one direction, and there is a friction force in the other direction, if we do a free body diagram, it doesn't want to do it for me. There we go. That friction force is going to be equal but opposite. Now we have a gravitational force pulling down as well as a normal force pushing up from the surface. If we have a horizontal surface, and the book likes to use just N for normal force, I like to use F sub N, F sub G. This is F applied, and this is F S or F K. If it's S, it's stationary, static. And mu S is taken when we have the ratio of Fs over Fn. All right. If we look at a kinetic friction situation, that looks identical basically to this, except for the fact that we have a kinetic friction force. So that is Fk. So mu k is Fk over Fn. Now, if we have a horizontal surface, Fn is equal to an opposite Fg, the weight. All right. And the force of friction is equal to an opposite the force that we pull or push something with. So when we test friction, we usually pull and measure how much force it takes to move it and how much force it takes to keep it moving at a constant rate. Because if we do it at an accelerating rate, that means we're putting more net force in than there is friction. And we measure that force, and we also measure the weight. And if it takes more force to pull it than it does to lift it, the mu is less than 1. All right. So our coefficients of friction, here is a diagram of the kinetic friction, the weight, and the normal force. The book uses W and N for weight and normal, and the applied force to the right, and we get a velocity. Now, notice, it doesn't matter if we double the weight, because that doubles the normal force. It will cause us to have to use double of the force to get the same velocity. In other words, it's a ratio. So the ratios stay the same depending on the substances that are in contact with each other. So we have a variety of different combinations that we look at. You can't look at one substance and say it's got a certain coefficient of friction. It has to be, what are the two substances together? So rubber on concrete, your tires have a coefficient of friction of 0.8 for kinetic and 1 to 4 for static. That means it takes, if you have a car that weighs 10,000 newtons, it takes 10,000 of 40,000 newtons to start your tires sliding. All right, that's static. But it takes only 8,000 newtons to keep them sliding. So we all know that once something starts sliding, it's easier to keep it sliding than it is to start it sliding. If you've ever pushed something, once it gets moving, it's easier to keep it moving. That one of the reasons is because of inertia, but another reason is because the kinetic friction is always less than the maximum static friction. So you're always going to have an increase in force in static friction until it breaks free, and then the amount of force necessary to keep it moving is less than the maximum. So you can see the right-hand column here, the static friction force is more than the middle column, the kinetic friction coefficient. And these are just ratios. So I like to think of it, if I have 100 newtons worth of force to cause a steel cabinet to move across a steel floor, I need to put 74 newtons of force to start it sliding and only 57 newtons of force to keep it sliding. If I have steel on ice skates, all right? Ice skates are quite low friction. So it only takes, if I weigh 100 newtons, it only takes 10 newtons to start sliding the steel across and only 6 newtons to keep it moving. If you are a skier or a snowboarder, we can see that when waxing the skis, it takes very little friction. So the smaller the coefficient of friction, the more slippery the two surfaces are with each other. The larger the coefficient of friction, the more sticky they are in sliding against each other. Teflon is the lowest friction man-made substance that we've ever made. And we can see here that Teflon on Teflon is 0.04 for static and 0.04 for kinetic. Now, this is only in a 1 sig fig. If we went to multiple sig figs, it would probably be more for static and a little bit less for kinetic, but they round to 0.04. Human joints are even lower friction. So if you have grandparents or know anyone that has had a joint replacement, usually what they do is put Teflon on Teflon in there, and because that's really slippery materials. But you can see here that if we compare the actual joints of humans, it's about 4 times more force to slide Teflon and Teflon compared to the actual synovial joints, that the fluids in your knees or your joints in your hip. So it does take more effort to move artificial joints than it does to move natural joints, unless there's damage and arthritis and different things like that. And it really decreases once it's moving. So we don't really feel, those of us that are young enough don't really feel a lot of resistance when we start moving. But as people age and get arthritis and stuff, when they get a hip replacement or a knee replacement, they notice that they're not in nearly as much pain, and they can walk and move with less effort because of that decrease in the friction by using the Teflon. All right. So that's what I want to stop with there. Tomorrow we'll talk about. I'll do a video lab for you guys on friction, and then we'll have some talk with tension and connected objects. Thanks a lot. Have a great day.